Hi everyone, I'm David Green from Mineral Resources Tasmania. I'm a spectral geologist and I work mainly with the HyLogger instrument, and so that's where I'm coming from, but what I'm talking about will be generally applicable to portable instruments as well. I intend to go through an introduction to HyLogging, spectral geology, where we get the mineralogy from results from it, and then we'll have a rest, and then I'll go through a whole heap of quite varied examples to show you the sorts of things we can use it for. Okay, on with the show. HyLogging, it's a suite, it's a system of hardware and, very importantly, married software for looking at large amounts of hyperspectral data. And usually it's from drilled materials like diamond drill cores, rad drilling, but also you can do it on hand specimens, thin section blocks, all sorts of stuff. We can even do sort of semi two-dimensional material, but please don't ask us to do too much of that. It takes a long time. The outputs are logs. We can use them in mainly in the digital world, but very graphic in their output, and to be used in analog as well. And they do not replace human logging. They do augment it only. It's like adding a whole heap of infrared wavelengths to your visual system, that is your eyes. The rationale for HyLogging came about, well, it was instrument driven and needs driven. The instrument driven was that the CSIRO developed a hyperspectral system originally designed to fly on a satellite, but here it's being applied to fly over drill core. So drill core is an expensive thing to get, and when we log it, it's subjective, right? It's often unrewarding, and it's often given to junior staff. Okay, so we don't really get the most out of it this way, we believe. And the records of logging are not easily returned to, and they don't have much longevity because things change. So can we get more out of all this drill core? And we believe that drill logging hyperspectrally can give a heck of a lot more out of the drill core. So instead of taking drill core, whether it's stored not so well, or better, or best, turn it into digital information by scanning that will result in value-added results that are much more improved. Now, the infrared system is how we do this. It gets the mineralogy, and the systems you tend to use in the field would be handheld instruments. Here's 3 of them. The 2 on the outside are for the shortwave infrared, and the middle one also handles the mid-infrared. So it's got, if you like, eyes that see more wavelengths, can see more types of minerals. So there are drill core imaging systems, and including the core scan, obviously, and an increasing number of competing systems in this space, including down the bottom right here, a portable logger which you just run over drill core that's in trays on the ground. The HyLogging system is not an imaging system. It just scans a single line down the middle of the core about 1 centimetre wide. It shines infrared light on the core, and it reflects off the core to 3 spectrometers, a visible and near infrared spectrometer, a shortwave infrared, and a thermal infrared spectrometer. It's the moving parts is just the tray moving around underneath these spectrometers in a predetermined pattern to cover all the core. You get 125 samples per meter. Each sample is about 10 by 18 millimeters. So you get a sample every 8 millimeters down the drill hole. So that's lots and lots of samples. A typical drill hole might have 50,000 samples. There's also high resolution normal imaging, if you like, line scan imaging that your eye can see. That proves it's valuable for users. And there is the Spectral Geologist, or TSG, software tied to this instrument. It's useful. You can use it for those portable instruments as well, and you can use it for core scan data, but it's currently it's tailored, if you like, to the HyLogging system. And HyLogging system is dependent on TSG, but not vice versa. The HyLogging facilities can be typically set up in a core library like this, and most geological surveys in Australia have them, as well as in Chile, China, and Mexico. Somewhat transportable when they're containerized, or smaller versions of HyLoggers can be put in a van even. This is the GeoLogger I showed earlier. That's sort of something in between a handheld analyzer and a fully fledged scanning instrument. Looking at the infrared. Okay, so this is what we see, this part of the electromagnetic spectrum in here, and the HyLogger basically gives us an augmented set of eyes to see things which are outside this wavelength. So minerals which might appear various shades of green in the visible light might appear to be, when we look at them in infrared light out here, they will be far more clearly distinguished from each other if we had eyes that could see those wavelengths. So the HyLogger sees the visible as well as the near infrared. So this bit here, visible, near infrared out to the shortwave infrared, and then it sees another band of wavelengths out in the thermal infrared, and there's a gap in between the mid infrared. And an upgrade to the HyLogger being managed by Core Scan will fill in this gap, so there will be a number of channels in here as well. So that's on the horizon. The idea of using infrared light is that it interacts with the minerals in a way which is highly characteristic of the mineral. So infrared light shines in or on to the target or the drill core, the mineral, and then the light goes in and it wanders around if it's shortwave infrared, and it bounces off and interacts with the components of the minerals, and then comes out and is detected by the detector. While it's in here, it either gets straight reflected, like here, so it came in, wandered around, came out again without much change, or it might be affected by the components of the mineralogy, and some of the light get absorbed at certain wavelengths, like this bit here, and that'll be characteristic of the minerals. And this particular mineral here, you can see that reflectivity generally drops off as the wavelength gets longer. And in the thermal infrared, we actually don't get any light coming back off the crystal, only we just get it in small amounts. So in this area, the light is actually interacting only with the very surface of the mineral. So in the shortwave infrared, the light goes in, bounces around a lot, and comes out and gets a chance to interact with all that volume of material. In the thermal infrared, it's only seeing the very surface of the sample medium, the drill core. What happens when the light goes in is that if it's a wavelength which resonates with the energy of vibrations in the molecular components of the crystal, then it will absorb. So here we have an asymmetric stretch of between the oxygen and hydrogen elements of a crystal, and here's a symmetrical stretch, and over here a bending, symmetrical bend, and all these will have different energies related to them, and so different wavelengths of light will be absorbed when they are the same wavelength as corresponds to the energies of these vibrations. And so that results in absorption of the light. So when we get that resonance, the light gets absorbed, and it will be re-emitted as heat or something, but we don't see it. And so these absorptions relate to these fundamental vibration characteristics of the crystal. Okay, so those vibrations and the absorptions associated with them occur fundamentally at thermal infrared wavelengths, And when we go to shorter wavelengths, what we're seeing is combinations of those features. So a simple feature in the thermal infrared, a number of them will be combined by simple addition, by resonance in the mid-infrared. And by the time we get up to the shortwave infrared, what we're seeing is combinations of vibrations and overtones of those, and then overtones of those and overtones of those. So these things are repetitions up here of the shorter wavelengths. So what we see are quite complex features. We can understand them, the details of them, by all these things are characterized. We understand the crystal structure, and to a degree we might be able to assign certain the parts of a spectral feature with its components which have been combined. So here we might have a bending and a stretching of the aluminium oxygen hydrogen feature in a molecule, and all these different bits and pieces of absorptions get combined in a complicated feature. So although these things are known, what we really get at the end is a characteristic infrared spectrum of a mineral, and these spectra will differ from mineral to mineral. Another type of process which results in absorption of infrared light is when we're dealing with elements with parts of the crystal which are characterized by electrons in metallic type orbitals. And these result in absorptions which are much broader. So those absorptions we saw before with bendings and stretchings will be very narrow absorptions. Okay, they occur over narrow wavelengths. These crystal field ones occur over wider wavelengths. We tend to get these with things associated with metals. So things like hematite and goethite will have absorptions like this, where we have lots of iron in the mineral. And another type of absorption is this unusual one, I think, related to rare earth oxides, which case, and where the atoms of these rare earths interact with the light in a way that give very, very narrow and sharp absorption features, which can be seen directly. So we're actually looking at the atoms themselves, atomic proportions, not molecular components or bonding components within the crystal, as we saw earlier. So those are the three types of absorptions that we see in the infrared. And some minerals have absorptions which here go all the way through. There are absorptions, characteristic absorptions through the visible and near infrared, through the shortwave infrared, and then continue with absorptions and reflections. Reflections is a simplification, sorry, but they look a bit like reflections coming back and out in the thermal infrared. Other minerals don't have much happening in the shortwave infrared, and all the action occurs in the thermal infrared. And generally, the minerals which we can see better in the shortwave are oxides and hydroxides, and in the thermal infrared are anhydrous silicates. Here's the HyLogger. Lots of channels. It's the secret to its works is the liquid nitrogen cooling, which increases the signal to noise ratio, so that a handheld instrument it takes maybe 30 seconds to take a spectrum, but here we get a spectrum every 1/12 of a second, and it does that because it's got very, very sensitive electronics and detectors. The instrument has a laser profilometer measuring the height of the drill core. That's chiefly used to work out where there is actually core. When there's no core, it assists with the automatic processing, and it includes a high resolution, that's 0.1 millimeter line scan camera at the normal visible wavelengths, RGB. The footprint of the spectrometers, it sees 10 millimeters by 10 millimeters, but the core is moving in a scanning mode, and so it will get stretched out. So you finish up with something like an 18 millimeter footprint, but we take our sample every 8 millimeters. So there's a fair degree of overlap between samples. Just reviewing quickly, the target of the HyLogging system, scanning like 125 samples per meter, 8mm samples, the main thing is this objectivity we get, okay, and we get consistency. So even if it's not 100% correct, it's at least comparable. Okay? We get a very high sample density, which gives you increased confidence. We don't have to handle the core very much. They're just scanned in the original trays, and there's not no sample preparation. We'd like them to be dry. We don't particularly want them to be particularly rusty, because we're just seeing mainly the minerals that are on the surface of the core, and if it's covered in crap, that's going to interfere. So crap meaning dust, rust, going off, that sort of thing. Geologists can use the HyLogging results as a basis for further work, and use their talents to where they're more suited, not just basic identification of minerals. And where there's new knowledge in the spectra, we can see things that you wouldn't see otherwise with a human eye. Okay, so all minerals that are kind of a yellowy white color aren't the same, but they're very, very different. For the HyLogger, it can tell illite from kaolinite from white mica quite easily. And the whole thing is can be archived very easily, in our case the National Virtual Core Library, but anything digital can be archived in this way, and it lends itself to applications which are long-term, so therefore the same information can be used in the exploration, then during mining, and then much later on in environmental management and rehabilitation, all sorts of things. So you can come back to as you do come back to the drill core time after time, you can come back to the HyLogging information time after time to get more and more out of it. In relation to other tools, we are looking at mineralogy here. So it's the minerals and their composition. In no way are we looking at elemental composition. Okay, so it's complementary to the geochemical methods, right? And it requires no sample preparation, and it's fast. We can do, 4 meters in 5 minutes, so you can do 400 meters in a day if you really wanted to. So that's pretty good. You get a huge amount of oversampling. Like a drill hole will give you 50,000, 100,000 samples, and there's a lot of statistics in there which give you a lot of confidence in what's going on. So an individual spectrum by itself may not be 100% confident about it, but when you've got 100,000 of them, you can certainly see the trends. We only get relative proportions of the minerals, not the modal abundances. It's not calibrated against anything. So when if we see in the spectra that a rock is 50% chlorite and 50% muscovite, it may not be correct. It could be 70% muscovite and 30% chlorite. But the changes going down a hole and between holes will be okay. You can calibrate it, and you can use rules of thumb to convert apparent modal abundances to real ones. Now the HyLogger can see some minerals that are really hard to see otherwise. So and the shortwave wavelengths, as I said earlier, they go into the rock, interact with it, and come out. So the light will go in, say a quartz crystal, and it will bounce around inside of there and come out again. And all of the light that goes in will come out. But if there's little bits of tiny little trace amounts of white mica in that quartz, that light bouncing around is bouncing around so much that it will get the imprint. It'll interact with the white mica, and certain parts of the spectrum will be absorbed, characteristic of that white mica. And so you will see the white mica in that rock, and it might look like a very strong influence because there's nothing else in there. So even though it's mainly quartz, because the quartz doesn't interact with the light at all, it's just transparent for the shortwave infrared anyway. But the thermal infrared, quartz is now the infrared light, thermal infrared light will hit the surface of it and interact, and we'll get a very large percentage of bouncing off. So none of the light actually gets in. So the thermal infrared can see something a little bit different from the shortwave infrared, which is measuring more of a volume. In fact, how much does it see? Well, the indication is just how much visible light goes into something. So if a mineral appears semi-transparent with your eyes, then it's probably semi-transparent for the shortwave infrared. So that's the volume it's sampling, a lot, millimeters. And as HyLogging is objective, operates the same way day in, day out, the same instrument and across instruments all over the world. What can we see? Well, we see iron group minerals, we see muscovites, kaolinites, smectites, sulfates. We can see silica, but only by the water features, which we see a spectrum of water. And when we see just water by itself, that usually indicates that we're seeing quartz with fluid inclusions. Alunites, chlorites and amphiboles, carbonates, and epidote prehnite tourmaline, importantly zeolites, and to a degree some sulfides with the visible area. In the thermal infrared, we add a whole heap more, pretty much everything else. We see all the feldspars, quartz, pyroxenes, olivines, garnets, apatite, barite, and everything else that we saw in the shortwave infrared repeated, as well as in some zircon, vesuvianite, all sorts of interesting things. So the thermal infrared offers a lot more. Of course, it means that the unmixing task is more complicated. Moving on to the software, before we finish off this introductory section, the spectral geologist is a very powerful piece of software for dealing with spectral data. It can deal with hand specimens, so you might have 20 samples and it'll deal with them very well. It can deal just as well with 100,000 samples at the same go. At the top here is these are the different ways of looking at TSG, the screens that it uses. I'll just go through them one by one quickly. The summary screen is that summary here. It's a histogram down the drill hole, showing relative proportions as far as the spectra are concerned of the minerals. And here it's doing it in 1 meter bins, which is set over here. And the yellow is muscovite and the green is chlorite. So the ratio of muscovite to chlorite varies here and there all the way down. This area here, it's more like 50-50. But up here, it's more like 90-10 or something. This area here with grey is aspectral, probably black shale, which very little reflectance. The blue is carbonate, and the browny colour is sulfates. Down the bottom, we have the thermal infrared interpretation. So although the muscovites and chlorites and so forth are still there, they're actually dwarfed in comparison to how much quartz there is and feldspar in the pink and the brown. So the muscovite is really, even though it's 90% of the rock as far as the shortwave is concerned, and as far as the thermal is concerned, it's only 10% of the rock. Most of the rock is actually, it's more like 50% quartz and 30% or so of plagioclase. So the bottom plot here is more reflective, I think that might be a pun, of the modal composition of the core than the shortwave infrared. But the shortwave infrared is very sensitive to minerals which are of particular interests to exploration geologists and operation geology. So some very important minerals are here. So this remains highlighted like this. The next screen is a log screen where we see every 8 millimeters down the drill hole and individually how the spectra have been interpreted into unmixed into minerals, and that unmixing occurs, you can see in the various ways. There's an automatic unmixing, which gives you results, which in this case is called the system. TSA is the spectral assistant for the shortwave infrared. So this is the system interpretation of the spectral assistant in the shortwave, and then for the TIR and for the visible. So there's an automatic result straight out of the machine. You can constrain the minerals available to the unmixing based on detailed spectral analysis, possibly geologically unlikely minerals, but spectral analysis is the way to go. You finish up with the spectral analyst SWIR results, and the same for thermal and visible. And a further refinement, we can use a restricted mineral set for different parts of each drill hole. So this is the domains of the drill hole. So domained, the spectral assistant shortwave infrared. And there's another algorithm there to complement TSA called CLS, and that's typically used in the thermal infrared. So all of these are unmixing algorithms, varieties of unmixing algorithms which give you results. So the automatic to user intervened, if you like, and then with further refined to give you these domained ones. So they get hopefully better and better interpretation as you go down there. We can see spectra here now, a spectrum, individual unknown spectrum in green and a library spectrum in pink, and we can see how well either our manual or automatic interpretation is doing to see if the spectral features of the library match the unknown. We might interpret that that mineral is actually in there. Here's a stack of spectra, most useful for hand specimens. And scatter screens are the workhorse of TSG. In this case, I've got here a scatter diagram showing the wavelength of a white mica feature corresponding to the ALOH absorptions associated with ALOH part of the crystal, and that wavelength is related to the composition of the white mica. The short wavelengths are more aluminium rich, more end-member white muscovite, and the longer wavelengths more phengitic, magnesium ion, silicon richer. Things can be presented as histograms. We can stack spectra, we can show density diagrams, all sorts of things are possible in scatter diagrams. Including looking at the color of the core. This top one here is the accentuated color. So down here, if you went out and looked at this boundary in the core, it might all look the same color, but guided by the spectral geologist here, we might be able to see, oh yeah, this bit down here is a little bluey gray, whereas the stuff above it is slightly greeny gray. And so you can get your eyes into the shades of core in a fairly objective manner, being guided by this. And these bottom plots here, we're assigning artificial colors down the hole corresponding to different minerals. The tray screen, we can look at individual trays sequentially, and we can plot different scalars, we call them, quantitative things. So I could, for instance, show the details of the mineralogy tray by tray as we go down in this sort of fashion. And we can, the equivalent of scatter screens in a vertical view is the whole screen. I prefer the scatter screen mainly because it's the aspect ratio of a computer screen lens drill quarter lying on its side. And the last one, PLS, is for modeling things quantitatively. So it uses partial least squares to use the spectra to model something which we have training data for. In this case, it's modeling sulfide totals. These are other products you can get out of TSG, include the line scan imagery, really valuable by itself, either as close-ups, like here, whole sticks of core. You produce core images as well, in this case trays, and even the whole drill hole, like so. And we can handle chips, and you can see a whole drill hole pretty quickly like that. And all that's all out of straight out of TSG. So that's the basics of HyLogging spectral geology. I'm going to have a rest for well, I'm planning on 5 minutes, but let's just see what the boss has to say. Okay.